Okay, let's dive into this stack of source material. We're pulling insights from a textbook chapter that gets right to the absolute bedrock of using statistics for business decisions, how you define the data you need, and how you collect it.
Exactly. It's sort of understanding the raw materials, the ingredients, before you even start thinking about cooking up some analysis.
Right.
And it's part of that essential DZOVA framework: define, collect, organize, visualize, analyze. And honestly, if you mess up those first two steps, define and collect, well, the rest is built on shaky ground,
Yeah, your fancy analysis won't mean much if the data itself is flawed.
pretty much.
So our mission today is to unpack these fundamentals. What exactly are we trying to measure? How do we measure it? Where do we find this information?
And crucially,
And critically, because we can almost never gather all the data, how do we strategically pick a sample? And what are the critical, sometimes sneaky errors we have to watch out for when we're collecting?
yeah, pitfalls are everywhere if you're not careful.
We'll even look at a famous historical blunder that completely changed the game for data collection.
Oh, yeah, it's a classic, powerful reminder of why these basic concepts matter so much. So let's start at the very beginning, defining the variables you need to study.
Right. The source uses the example of a company like GT&M needing to figure out a fair price to buy another business.
Uh-huh.
To do that, you first have to decide what pieces of information are relevant: sales figures, costs, maybe customer demographics. These are your variables.
And defining them clearly is, well, it's non-negotiable. The type of variable you have fundamentally dictates the statistical methods you can use later.
How so?
Well, you just can't apply the same math to categories like yes or no as you would to pure numbers, like sales figures. The math is different.
Makes sense. And the material points to two main types: categorical and numerical.
Right. Categorical, sometimes called qualitative, are where values just fall into groups or categories. Think yes or no on a survey question. Or classifying students as freshman, sophomore, junior, or senior. There's no quantity implied, just different bins.
Okay, category. So numerical or quantitative, that's where we're representing actual quantity.
Exactly. And the source then breaks those down further into discrete and continuous.
Okay, what's the key difference there?
It really comes down to how you get the number. Discrete numerical variables result from a counting process.
Counting.
Yeah, the values are typically whole, finite numbers. Like counting the number of premium cable channels subscribed to, you get 0, 1, 2, etc. Or the number of items purchased. You can list out the possible values, usually.
Got it. Counting for discrete
Yeah.
and continuous.
Continuous numerical variables come from a measuring process. So the value can be any point within a continuum or interval,
Any value.
depending on how precise your measurement tool is. Think the time you wait for teller service, it could be 1 minute, 1.3 minutes, 1.358 minutes, whatever.
Oh, like file download time.
Exactly. These aren't restricted to just whole numbers. They can take on, basically infinite values within a given range.
So counting versus measuring, that clears it up. The source also mentions that the same idea, like age, could potentially be treated as categorical.
Right, like putting people in age brackets, 20, 29, 30, 39.
Or numerical, like their exact age in years. It depends on the study's goal.
Absolutely. And that really highlights the need for a clear, specific operational definition for each variable you plan to collect data on. What exactly are you measuring or counting, and how? You've got to nail that down.
Okay, so we've defined what we need to measure. We understand the variable type: categorical or numerical, discrete or continuous. But variables can be measured in different ways too, right? With different levels of detail.
Exactly. That brings us to measurement scales. They give you structure and dictate the level of information you capture, which again impacts your statistical options down the line.
And for categorical variables, the source mentions nominal and ordinal scales.
Yeah. Nominal is the simplest. It just names or labels categories with no inherent order or ranking.
No order.
None at all. Your favorite soft drink, political party, gender, or a simple yes-no question like, do you have a Facebook profile? Those are nominal. You're just putting data into distinct bins. It's the weakest level of measurement, really.
And ordinal adds, well, order.
Precisely. Ordinal scales classify values into distinct categories where ranking is implied. Customer service ratings like excellent, very good, fair, poor fit here.
Okay, so you know excellent is better than good.
Right, but you can't really quantify how much better. The distance isn't necessarily equal. Student class designation, freshmen to seniors, another classic ordinal example. There's a clear order.
Yeah.
But the gap between freshman and sophomore isn't necessarily the same size as between junior and senior,
Okay, so categories with no order versus categories with n order. Now, for numerical variables, we get into interval and ratio scales. These seem, well, more powerful.
They are. They capture more information. Interval scales are ordered, like ordinal, but the difference between measurements is meaningful and consistent.
Okay, the difference matters.
Yes, but there's no true 0 point.
Yeah.
Temperature in Celsius or Fahrenheit is the classic example. The difference between 20 and 30 degrees is the same jump as between 70 and 80 degrees.
Right, 10 degrees.
But 0 degrees Fahrenheit doesn't mean no heat at all. It's just an arbitrary point on the scale. So you can't say 60 degrees air is twice as hot as 30 degrees Fahrenheit. That ratio doesn't work.
Ah, okay.
Test scores, like ACT or SAT, often fall into this interval category too.
So differences make sense, but ratios based on 0 don't, because 0 isn't a true none.
Correct. Which brings us to the ratio scale. This is the highest level of measurement. It's ordered, differences are meaningful, and there is a true 0 point.
A real 0.
A real 0, meaning the complete absence of the quantity. Think height, weight, age, salary cost, file download time. 0 means none of it. 0 salary means no salary.
And because there's a true 0.
You can make meaningful ratios. $1,000 is twice as much as $500. 0 download time means instantaneous. The source contrasts Fahrenheit Celsius, which are interval scales with arbitrary zeros, with the Kelvin temperature scale.
Kelvin.
Which is a ratio scale because it's 0 point, absolute 0, means the true absence of thermal energy.
Wow, okay. That true 0 point makes a huge difference in what kind of comparisons you can legitimately make. So understanding these scales tells us how much information our numbers actually contain and what calculations are okay to do.
Exactly.
That pretty much covers the define part, knowing what we need and how we can measure it. Now on to collect, getting the data itself.
And this is where, quality control really starts. The source rightly points out that collecting flawed data will inevitably lead to suspect results.
The old garbage in, garbage out problem.
Absolutely. It applies strongly here.
So where do we even begin to look for this data?
Well, data can be primary, meaning you collected it yourself for your specific purpose, or it can be secondary, meaning someone else collected it, maybe for a different reason, and you're just using it.
Reusing data.
Right. And collection methods, they really range widely. You could run designed experiments, get responses from surveys, conduct observational studies like focus groups, all the way to data that's just captured by ongoing business activities.
Ongoing business activities.
Yeah.
That sounds like where a lot of modern data comes from, right?
It absolutely is. Think about transactional data from sales systems, website click streams, social media interactions, app usage logs, that sort of thing.
Yeah.
These are major sources of what we now call big data. A company might analyze their internal sales data, which is primary,
Right.
and maybe combine it with social media sentiment data they purchased from another company, which would be secondary.
Okay, so lots of places to find data, but we rarely get data from everyone or everything relevant, which brings us to populations and samples.
Right. The population is the entire group of items or individuals you want to draw conclusions about.
The whole enchilada.
Exactly. If GTM wants to understand all their sales, the population is all their sales transactions for the relevant period, every single one.
And a sample is just a portion of that population, the subset you actually select and analyze.
Yep. The source uses a great analogy.
Okay.
The population is the whole pie, and the sample is just a slice you take to taste.
Pie. So why use a sample? Why not just look at the whole population?
Well, the practical reality is that collecting data from an entire population is often just too time-consuming, way too costly, or sometimes simply impossible.
Too big, too messy.
Yeah. So we work with samples to make inferences about the whole population.
Okay. Now, before we jump into analyzing that sample data, the source mentions steps like data cleaning and recoding. Are those important?
Oh, definitely. Data cleaning is basically about housekeeping for your data. It involves identifying and handling irregularities, things like errors, missing values, or outliers.
Outlier.
Yeah, those values that seem really far removed from the others, maybe a data entry mistake, maybe something genuinely unusual. Cleaning is about making the data usable and reliable.
Okay. Fixing the mess. And recoding variables.
Recoding is when you create new variables from existing ones. For example, you might take a numerical variable like exact age and group it into age brackets like Under 30, 30, 50, over 50.
So turning numerical into categorical.
Exactly. Or you might combine several detailed categories into fewer, broader ones.
And when you recode, you have to make sure your new categories don't overlap and include everything, right?
Absolutely crucial. They must be mutually exclusive,
No.
meaning each original data point fits into one and only one new category. No ambiguity.
Got it.
And they must be collectively exhaustive, meaning the new categories together cover all the possible data points you're recoding. Nobody gets left out.
Okay. Mutually exclusive and collectively exhaustive. Makes sense. So we know what variables, how they're measured, where to find data, the population versus sample distinction, and these cleaning coding steps. Now, how do we actually pick that piece, that sample? This seems critical.
Oh, it is. This is where sampling methods come in. And it all starts with the frame.
The frame.
The frame is essentially the list or source from which you'll actually draw your sample items. It could be a list of all registered voters, a list of all employees, a directory of businesses.
Okay, the source list.
And the source provides a critical warning here. An inadequate frame, one that doesn't truly represent your target population, can build bias into your study from the very beginning, before you even pick anyone.
Right. If your list is bad, your sample drawn from it will be bad.
Exactly. Now, there's a big divide in sampling methods: non-probability samples and probability samples. And this distinction is incredibly important.
Why is that?
Because only with probability samples, where every single item in the frame has a known non-zero chance of being selected, can you use statistical methods to make valid inferences and generalize your findings from the sample back to the entire population.
So only probability samples let you make those bigger claims.
That's the key. Non-probability samples don't offer that statistical capability.
Okay, let's talk about non-probability samples first then. What are there? The source mentions convenience and judgment samples.
Right. A convenient sample is pretty much what it sounds like: selecting items that are easiest to reach or sample.
Like grabbing the first 20 people you see.
Exactly. Or using responses from an online survey where anyone can click an answer. It's quick, it's cheap, but the group you get is often self-selected or just happens to be there. It's not necessarily representative of anything larger.
Okay, easy, but maybe not representative. What about a judgment sample?
That's where you select items based on the opinion of experts who believe those items are representative of the population.
So relying on expert intuition.
Yeah. Again, maybe convenient, maybe useful for exploratory stuff, but you can't statistically project those opinions or findings to the broader population. The main takeaway for both convenience and judgment samples: use them maybe for quick insights, preliminary work, idea generation.
But don't.
But do not use them to make statistical claims about a larger population. The potential for serious bias is just too high.
Okay, so for reliable, generalizable results, we absolutely need probability samples. The source details 4 main types: simple random, systematic, stratified, and cluster sampling. Let's start with simple random.
Simple random sample, or SRS, is sort of the gold standard conceptually. In SRS, every single item in the frame has an equal chance of being selected.
Equal chance.
And not only that, every possible sample of the desired size, let's say picking 100 people out of 1,000,
Yeah.
have an equal chance of being the sample that gets selected.
Truly random.
Truly random. You can sample with replacement, meaning an item could theoretically be picked more than once, or without replacement, which is more common, where once an item is picked, it's out. The source mentions using random number generators or tables for rigorous selection.
Okay. Sounds ideal theoretically, but maybe hard to do with a huge list.
It can be logistically challenging, yeah.
Yeah.
Which leads to systematic sample.
How does that work?
Here, you first decide your sample size, say n from your frame size, n. You calculate an interval k by dividing n by n. Then you select a random starting point somewhere within the first k items on your list.
Random start.
And then you select every k item after that, all the way down the list.
Like pick number 7, then 17, then 27 if k is 10.
Exactly. It's often simpler and faster than simple random sampling, especially if you just have a physical list. But there's a catch.
What's the risk?
You need to be careful if there's any kind of periodic pattern or cycle in your list that happens to line up with your sampling interval k. If that happens, you could get a really biased, unrepresentative sample.
Interesting. Easier, but potentially risky if the data has a hidden pattern. Okay, next up, stratified sample. This sounds like dividing the population up first.
That's exactly right. With stratified sampling, you first divide the population frame into subgroups called strata. These strata are based on some shared characteristic that's relevant to your study, maybe age groups, income levels, gender, geographic regions, whatever makes sense.
Okay, divide into groups. Then what?
Then you take a simple random sample from within each stratum.
You sample from each group separately. Why go through that extra step?
Two main reasons. First, it guarantees representation from all those important subgroups. If you just did a simple random sample, you might, by chance, miss getting enough people from a small but important group. Stratifying prevents that.
Ensures diversity in a way.
Right. And second, it can often provide more precise estimates for the overall population compared to simple random sampling, especially if the items within each stratum are more similar to each other than they are to items in other strata. The source uses a university example, stratifying students by both gender and class designation, like freshman male, freshman female, sophomore male, etc., before sampling within each of those cells.
So stratified ensures representation across predefined groups by sampling within each. How does cluster sample differ?
Cluster sampling also involves dividing the frame into groups, called clusters. But these clusters are usually naturally occurring groups, often based on geography or some physical grouping. Think city blocks, zip codes, schools within a district, or maybe dormitories on a campus.
Natural groups, okay.
Then, instead of sampling individuals from all groups, like in stratified sampling, you take a random sample of the clusters themselves.
You sample the groups, not the people.
You randomly select some of the groups. And once a cluster is selected, you typically collect data from all the items or individuals within that selected cluster.
Oh, okay. So you randomly pick, say, 5 dorms out of 30, and then survey everyone in those 5 dorms.
Exactly. This can be much more cost-effective and practical, especially for populations that are spread out geographically. Imagine trying to do a simple random sample of residents across an entire state versus randomly selecting a few counties, the clusters, and surveying everyone within those selected counties.
Way cheaper, probably.
Often, yes. The trade-off is that you might need a larger overall sample size with cluster sampling to achieve the same level of precision as you'd get with simple random or stratified sampling. That's because items within a cluster might be more similar to each other, like people on the same block, than items chosen completely randomly.
Got it. So several different probability methods, each with pros and cons depending on the situation. But even if you use one of these proper methods, especially with surveys, things can still go wrong, can't they? The source talks about potential survey errors.
This is absolutely critical to understand, yes. These errors can undermine your results even if you started with a perfect probability sample design. The source outlines 4 main types. First up is coverage error.
What does that mean exactly?
Coverage error happens when your sampling frame, that list you're drawing your sample from, doesn't completely cover the population you actually want to study. Certain groups are excluded right from the start.
So the list itself is incomplete.
Right. Your sample then can only represent the frame it was drawn from, not the true population you were aiming for. A classic example is using a list of landline phone numbers to survey everyone in a city. You're automatically excluding anyone who only uses a cell phone or has no phone. That's coverage error.
Got it. The frame doesn't fully cover the population. What's next? Non-response error.
This is a huge one. Non-response error occurs when you fail to collect data from all the individuals you did select for your sample.
People just don't answer.
Yeah, they might refuse to participate. Or maybe you just can't reach them after multiple attempts. The error part comes in if the characteristics of the people who do respond are systematically different from the characteristics of those who don't respond.
So the results are skewed because only a certain type of person answered.
Precisely. That's non-response bias. It's why survey researchers often put a lot of effort into follow-up attempts to minimize this.
That difference between responders and non-responders seems really problematic. What about sampling error? Is that different?
Yes. Sampling error is fundamentally different. It's simply the inherent chance variation that exists between any sample and the true population, just because you're looking at a subset rather than the whole thing.
Just luck of the draw.
Pretty much.
Yeah.
It's the luck of the draw in which specific individuals happen to end up in your particular sample versus another sample you might have drawn.
Yeah.
This is actually the error that the margin of error in political polls tries to quantify.
The plus or minus 3% thing?
Exactly. You can generally reduce sampling error by using a larger sample size, but you can't eliminate it entirely as long as you're sampling. It's a natural consequence of not measuring everyone.
Okay, so sampling error is just the natural wiggle room from using a sample. Doesn't sound like a mistake in the same way as the others. Finally, measurement error.
Measurement error happens when the data you do collect doesn't accurately reflect the true value or opinion you're trying to measure.
How can that happen?
Oh, lots of ways. It could be due to flawed survey questions. Maybe they're vague, or they ask two things at once, double-barreled, or the wording is leading. It could be the way the survey is administered. Maybe the interviewer influences responses, or people give socially desirable answers. Or it could be the respondent themselves. Maybe they misunderstand the question, have memory lapses, or even deliberately give a wrong answer. It's about problems in the measurement process itself, not about who was or wasn't included or responded.
Wow, so many potential pitfalls. Coverage, non-response, sampling, measurement. It's a minefield. And the source even touches on how these errors can become ethical issues.
Yes, unfortunately, particularly when bias is introduced, not just by accident, but maybe deliberately.
Like how?
Well, things like purposely creating a sampling frame that excludes certain groups you don't want to hear from, or designing questions that subtly nudge respondents towards a particular answer favored by the sponsor, or maybe presenting results from a non-probability sample, like a website poll, as if they represent a whole population without clearly stating the huge limitations.
Misleading people.
Exactly. Or even on the respondent side, people providing deliberately false information. These aren't just statistical problems. They really impact the integrity and trustworthiness of the conclusions drawn from data.
Okay, here's where it gets really interesting, and where we see these errors play out on a massive, very public stage. The source brings up the classic example of the Literary Digest presidential poll in 1936. Tell us about that.
The Literary Digest. This was a huge, well-respected magazine at the time. And they conducted this massive poll for the 1936 presidential election between Franklin D. Roosevelt, FDR, and Alf Landon.
How massive?
They sent out something like 10 million ballots, mock ballots, mostly to people on lists derived from telephone directories and automobile registrations. And they got back over 2.3 million responses, an enormous sample size, especially for that era.
Okay, huge sample. What did they predict?
Based on this massive return, they confidently predicted that the Republican candidate, Alf Landon, would defeat the incumbent Democrat, FDR, quite handily.
Except, that's not what happened, right?
Not even close. FDR won re-election in one of the biggest landslide victories in U.S. presidential history. The Literary Digest poll was spectacularly historically wrong.
Wow, what went wrong? That huge sample size didn't help.
It was a defining moment, really. It showed dramatically that size isn't everything. For a long time, the primary explanation focused on coverage error.
The lists they used.
Exactly. In 1936, during the Great Depression, owning a telephone or a car was much more common among wealthier individuals. Those lists disproportionately represented richer voters and excluded large numbers of poorer citizens.
Who were much more likely to support Roosevelt and his New Deal policies.
Precisely. So their sampling frame was severely biased and didn't accurately cover the actual voting population.
Okay, so that's a big problem right there. Bad frame.
That was certainly a significant factor. But later analyses, as the source notes, suggested that non-response error might have been an even bigger or at least equally damaging factor.
How so?
Well, think about it. They sent out 10 million ballots, but only got 2.3 million back. That's less than a 25% response rate. The analysis suggests that even among the relatively wealthier people who did receive the ballots, FDR supporters were much less likely to bother filling out and mailing back the ballot compared to the Landon supporters, who were perhaps more energized against FDR.
So the people who did respond were not representative even of the biased group who got the survey, let alone the entire voting population.
Exactly. It seems it was a devastating combination. A severe coverage error compounded by a massive non-response bias.
A double whammy. The source calls this a watershed event. Why?
Because it absolutely was. It powerfully, publicly disproved the naive notion that just getting a larger sample automatically means better, more accurate results.
Yeah.
A massive, biased sample is arguably worse than a smaller, carefully constructed representative one because its size gives a false sense of confidence.
Right.
This spectacular failure was a huge catalyst for the development and acceptance of more modern scientific polling techniques, like those pioneered by George Gallup, Elmo Roper, and others. They focused intensely on using probability sampling methods and smaller but much more representative samples and understanding and minimizing these kinds of errors.
And it's fascinating, isn't it, that the source draws a direct line from this 1936 disaster to some of the data collection we see happening today.
Yes, it's incredibly relevant. Think about many online surveys we encounter now, customer feedback forms that only pop up for certain users. polls on websites or social media feeds, email invitations to rate a recent purchase.
Yeah, we see those all the time.
While these methods can gather enormous amounts of data very quickly and cheaply, they often rely heavily on self-selected samples.
Yeah.
People choose whether or not to participate.
Right, like the Literary Digest respondents choosing whether to mail back the ballot.
Exactly the same principle.
Oh.
The source highlights that these modern methods, despite maybe having lots of data on the people who chose to respond, like demographics or purchase history, can suffer from the exact same kind of non-response error that sank the Literary Digest. You might have tons of data on the responders, but you usually know very little about the potentially vast majority who didn't respond. And if the non-responders are different, generalizing the results becomes incredibly risky.
So the lesson from 1936 about being incredibly careful with how you define your population, construct your frame, select your sample using probability methods, and anticipate these potential errors, it's just as relevant, maybe even more so, in the age of big data and instant online feedback.
Precisely. The tools change, the speed changes, the scale changes, but the fundamental principles of good, statistically sound data collection, they remain absolutely constant. If you ignore them, you risk being just as wrong as the Literary Digest, no matter how much data you have.
So we've journeyed today from the very first step of defining our variables and understanding the different ways they can be measured using nominal, ordinal, interval, and ratio scales,
The foundation.
to exploring where data actually comes from primary versus secondary sources, surveys, experiments, all those ongoing business activities generating big data. Then we looked at how to strategically sample that data using different probability methods like simple random, systematic, stratified, and cluster sampling.
Choosing your slice carefully.
And perhaps most importantly, we've unpacked those sneaky errors that can creep into the process, especially in surveys coverage, non-response, sampling, and measurement error. And that dramatic Literary Digest story really hammered home how devastating these errors can be. It's such a powerful reminder that the foundation, how you get your data, is absolutely paramount. Just having lots of data isn't enough.
Not at all. And thinking about that Literary Digest failure and its, direct echo in some modern data collection practices, it really does raise an important closing thought, doesn't it?
What's that?
Well, in a world just swimming in data collected from us constantly through pretty much every digital interaction, every app, every website, every loyalty program, are we as consumers, and maybe even as users or analysts of that data, paying enough attention anymore to these really fundamental statistical concepts we talked about today? Things like the frame, the actual sampling method used, the huge potential for non-response or measurement bias. Are we being critical enough to truly understand what all that data is really claiming to tell us?